I suggest to change the order of presentations because first talk is missing, then every talk will be shifted. I'm not sure if people will be happy about it. I would like to ask you, Christy, were you ready to give the first presentation? Because in that way we can keep the order of presentations.
Oh, sure. I would be happy to go first because it's 1:30 in the morning here, and then I can go to bed.
Yes. Yeah, I think, yeah. Why not?
Sure. Let me get my slides. Can you see them okay?
Yes.
Okay. Excellent.
Just one moment. I think we want to have about 20 minutes time for every talk. And then I think it will be reasonable. So if you talk something like 17 minutes, then 3 minutes for the questions, roughly. And then 2 minutes before your time will be over, I give you a sign. Then you know that how much time is left over here. Is it okay?
Yeah, that's fine.
Okay, fine.
Okay, wonderful. So I'm Christine Go. I'm speaking on behalf of the SWGO collaboration on the science perspectives of our detector. So what is SWGO? It's the Southern Wide Field Gamma Ray Observatory. It's a proposed future water Cherenkov experiment in the Southern Hemisphere for the ground-based detection of astrophysical gamma rays. No matter the final design choice, which you can see that there are several here, SWGO will similarly to the high altitude water Cherenkov or HAWK detector in the Northern Hemisphere detect air showers of particles produced by gamma rays hitting the Earth's atmosphere through the Cherenkov radiation produced by those particles in water for detection by PMTs. With an array of such detections, we can determine the energy and the direction of the incident gamma ray that hit the atmosphere and created the shower. And obviously we're still working on the specifics of the design. We could use tanks like HAWK, you can see up here, or a pond, perhaps even inside of a building like LASSO does, or a lake, either natural or artificial. We are also considering in this design adding muon tagging, which similarly produced by protons hitting the atmosphere instead of gamma rays. So by tagging the muons, this would help us differentiate the progenitor of the shower in question, whether it was gamma rays or protons. And really the question becomes in a field of detectors, how does this concept compare to the imaging air Cherenkov telescope arrays such as CTA, Veritas, or HESS? So you can see here that SWGO will have an incredibly wide field of view, about 90 degrees compared to the IACTs, which are only about 3 to 10 degrees, and near 100% duty cycle. This is also critical because the water Cherenkov design allows for observation night and day. We don't have the same kind of restrictions that IACTs do. The energy range is expected to get well above 100 TeV. And while angular and energy resolutions of IACTs are more precise, as you can see here, SWGO will be able to get down to an angular resolution of about 0.1 degrees at the highest energies and will really excel at observing extended sources. So the 5-year differential point source sensitivity is anticipated to be the best in the southern sky, above tens of TeV. Being the most sensitive observatory in the Southern Hemisphere in this energy range, above about 20 TeV, would make SWGO a really ideal complement, not only to Northern Hemisphere observatories, but also to CTA South. Its complementarity with Northern Hemisphere observations is well visualized by comparing SWGO's projected field of view with that of the HAWK observatory. So we can see that here. And the sky coverage of SWGO and galactic coordinates is shown by the red dashed line. And this is overlaid on the HAWK significance map. This map contains over 50 sources. And basically this shows that by placing SWGO in the Southern Hemisphere, we would have a prime view to monitor sources and source regions previously inaccessible or mostly inaccessible to HAWK, such as the galactic center and the Magellanic Clouds, as well as more ideal viewing of source regions such as the Fermi bubbles that HAWK has done extensive work on that SWGO could then improve upon. But really, if you want to learn more, especially about the detector itself and the bigger picture overall, there will be a plenary session on SWGO by Dr. Jim Hinton in session 2 on Saturday, and I encourage you to go and see that. But what I'll talk to you about today is the core science case that this design lends itself to in a really unique way. And this list is just an overview of the science we intend to do with SWGO once it's built, with really promising sensitivity studies currently being conducted on all fronts. So this includes transients, searches for pevitrons, gamma ray halos, fundamental physics, and cosmic rays. So jumping right in, the high energy transient sky. We anticipate being able to perform gravitational wave follow-ups. So GRB 170817 alpha and the subsequent kilonova emission associated with the binary neutron star merger for this launched the field of gravitational wave multi-messenger astronomy. SWGO could record real-time high energy gamma ray data for all gravitational wave events falling into its field of view. And this would allow us to provide real-time notifications to observatories like CTA so they could perform detailed follow-up observations. We also anticipate that we could look for high energy components of fast radio bursts. Monitoring approaches by IACTs of FRBs are less than ideal, as the duty cycle of FRBs is poorly constrained. So only a wide field of view survey instrument such as SWGO would be able to provide constraints on gamma ray emission in coincidence with bursts detected in the radio domain. And also from simulation studies, we expect that about 60 to 70% of FRBs are thought to be in the Southern Hemisphere. So a wide field of view telescope in the Southern Hemisphere would be ideal for the study of these objects. There's also been evidence for the interaction of high energy hadronic particles, and high energy neutrinos are really vital in the quest for sources of high energy cosmic ray accelerators. So being able to use a multi-messenger approach to determine the sources of these would be critical. And this really would allow the precise localization of the emission region, allowing for identification of the source, as well as information about the overall source energetics and energy and time-dependent power output. And very importantly, and I spoke about this a little bit yesterday with HAWK, but we really would be looking for very high energy emission from gamma ray bursts as well. So although electromagnetic emission from gamma ray bursts is widely observed down to the radio, the VHE domain remains largely uncharted. And the transient and unpredictable nature of GRBs combined with intrinsic alert delays by satellites makes it difficult for IACTs to observe GRBs rapidly enough to catch the prompt to early afterglow phases that favor VHE radiation. But SWGO's duty cycle would allow the monitoring of GRBs inside of its field of view, and this would increase the number of observations without the need for external triggers. In terms of galactic particle acceleration, we want the study of the galactic plane with VHE gamma rays is one of the most powerful methods to search for astrophysical particle accelerators, including pevitrons, and those being sources able to accelerate hadrons up to the knee of the cosmic ray spectrum, which I'll come back to the cosmic ray spectrum quite a bit later. But what we really want to do is search the galactic plane for these sources, and the design of SWGO is well equipped to handle source confusion, diffuse gamma ray backgrounds, spatially extended emission regions that would typically complicate these analyses. We want to be able to identify hard spectrum sources for long-term observation with CTA, and this will our observations will complement coverage of the Northern Hemisphere with HAWK and LASSO. And our large energy range, especially, and ideal design features like our high duty cycle. We're really enthusiastic that SWGO would be the optimal instrument to discover sources such as the microquasar SS433 observed by HAWK. So for pulsar wind nebula and gamma ray halos, first observed by HAWK, the all-sky observation of gamma ray halos, of which SWGO is capable, will allow testing of these really large gamma ray halos from potential sources for the observed positron excess, including millisecond pulsars. So studying gamma rays from potential positron sources provides crucial input to the positron excess puzzle. And we really, because these have such large angular extent, As I said before, that SWGO will really excel in looking at extended sources. This is where our instrument can really shine alone as the ideal monitor to do this. It will also allow potential discoveries of the millisecond pulsars, which are theorized but not yet discovered with current instruments. And then it would allow us to look both at the properties of accelerators and the medium around them. We can also look into the extragalactic very high energy sky. Very high energy gamma rays are expected from blazars and some radio galaxies. Pardon me. Several models currently exist to explain the spectrum of HE1 from radio to VHE gamma rays, with additional data needed to unravel the mechanisms that work within these environments. The VHE extragalactic sky is dominated by blazars, and we are expected to be able to detect VHE blazars at both short and long timescales, as well as perform searches in an unbiased way over the full southern sky. And this includes the extreme high energy peaked BL-LAX, for which our detector may be able to provide an unbiased sample of the closest of these TeV emitting sources based off of our design properties. So returning to the map of the sky that we would expect to see with SWGO, with the SWGO sky map shown here in gray, you can see that we get several prominent dark matter targets with this as well, that we could not see with HAWK, such as the galactic center, the Magellanic Clouds, and also these dwarf galaxies recently discovered with optical surveys like DES. And this would allow us to perform a wide variety of fundamental physics on these targets. So why would we even want to look for gamma rays to probe for dark matter? So WIMP dark matter can annihilate or decay to standard model particles, and these standard model particles can produce photons along with other particles. And this is through inverse competent scattering or photons off produced electron-positron pairs. And we'll also see this in another slide, but the really heavy WIMP models, masses of 10 TeV or greater, can be probed best with an indirect experiment such as SWGO. And so from this theory, we can search for WIMPs. The best and closest source is going to be the galactic center. It's a really dense region of dark matter. We can't really look for it with HAWK because it's right at the edge of our field of view. So SWGO in the southern hemisphere will be really ideal for this. And what we have here is the expected dark matter annihilation cross-section limits from the galactic center for Fermi-LAT and CTA and SWGO. And what you can see is that with all three of these instruments, you can cover the thermal WIMP cross-section from 5 GeV all the way up to 100 TeV, with SWGO being the experiment getting us all the way to 100 TeV. And then really notably, if the WIMP were to be a few TeV in mass, both SWGO and CTA would see it, and these multiple potential detections would be really important. This is one of the many exciting reasons to build SWGO. We could also look for axion-like particles since SWGO has the best sensitivity at the highest energies. What happens is a gamma ray can be emitted by a blazar, and then in the environment around that in the magnetic field, that gamma ray can convert into an axion-like particle. The cool thing about this is that axion-like particles do not attenuate on the EBL. So they just keep traveling, and then in the Milky Way, they can convert back into gamma rays in the galactic magnetic field. And what this gives you is this really high energy tail that you can see here. Normally with these extragalactic sources, they would be cut off because of attenuation on the EBL. But with axion-like particles, you get this tail, and that's something that SWGO would be sensitive to at the really highest energies. So like I mentioned before, we can also look for dark matter annihilation gamma ray from dwarf galaxies, which we've been discovering a bunch of those in the southern hemisphere. And by we, I mean the community, not SWGO. But this is the expectation of the limits that we could get if we had 30 dwarfs. And unlike similar experiments, we will have archival data at all locations that we can see on the sky, which means that if a new dwarf is discovered beyond the 30 proposed, we already have data on that source. It's also worth mentioning that with the wide field of view, SWGO would allow us to observe all of these dwarfs every single day. And this would give us a really nice survey of the sources needed to place such a limit. It's really definitely always worth mentioning Lorentz invariance violation. If Lorentz invariance is violated, photons will decay. And so if you're seeing a photon at, say, several PeV, this will set a limit on the energy scale of the Lorentz invariance violation. And we expect that SWGO will be sensitive up to gamma rays of a few several TeV, where the current highest energy gamma was very recently reported by LASO at around 1.14 PeV. And what we'll do is, so we would look at the highest energy gamma rays that anyone has ever looked at with SWGO. And that being able to detect gamma rays at these highest energies would allow us to place these limits on the LIV energy scale, which is the ELIV you see here. We can also look for primordial black holes, some masses of which are thought to be candidates for dark matter. PBHs are thought to be created in the early universe, and those that are at a original mass of about 5 × 10⁻14 grams, this is about the mass of the ice cube detector, are evaporating in the final seconds of their lives now through Hawking radiation. And this produces a burst of gamma rays, both primary and secondary. So with a wide field of view and a large duty cycle instrument, SWGO is really optimal to look for these PBHs because we don't know where they would be, but we could look at the entire sky. Currently, the strictest limits on primordial black holes has been set with Hawk, but we anticipate that the with our expected limits for SWGO, that we should be able to place constraints about 30 times better than that with our detector.
Minutes.
Okay. So for cosmic rays, the main feature in the energy spectrum of galactic cosmic rays is the so-called NE. And understanding the origin of the NE is really key for comprehensive theory of the origin of cosmic rays up to the highest observed energies. And really what the priority for a wide field of view instrument would be to measure the maximum acceleration energy in galactic sources to determine through the determination of NE energy in the proton primary spectrum, and investigate the origin of the NE, tracing the different components up to 10⁻16 electron volts, and measuring the cosmic ray anisotropy as a function of rigidity. With its wide aperture and almost 100% duty cycle, SWGO will be able to gather significantly larger electron event statistics than IACTs, which may help in extending the electron spectrum further than the 20 TeV already measured, potentially revealing more details about the local source distribution. So we hope to get much more detail on the cosmic TeV dipole sky map. This is the Hawk and ice cube combined shown, and we really hope that we'd be able to get more sensitivity than that. So in summary, SWGO is a proposed gamma ray observatory located in the Southern Hemisphere. They use the water Cherenkov technique to have the best sensitivity to the emission from high energy transients, gamma ray halos, pevitrons in the galactic plane, plenty of fundamental physics, including Lorentz invariance violation. Miigwech. And if you want to follow up on any of these specific topics, there are a bunch of ICRC talks.
Thank you very much, Christy. I think your timing was perfect. So please, question, comment, Christy. I have myself a question, Christy, to you. So in one of the first slides, you said you want to tag the muons, yeah?
Yes.
Yes, how it will be done?
We are considering using double layer water Cherenkov detectors. So this would be a time intensity tagging approach. So we would tag the particles in both the single, both the upper and the lower layer of the water Cherenkov detectors, and then use that to determine whether or not they were muons.
Essentially, it will increase the number of sensors for your detector. Yeah, I think the cost issue it will be, because then you will need to cover with sensors 2 layers.
Yes, but it is that's one of the things that we're considering. Is it worth it for the improvements that we would get by really being able to rigidly differentiate the progenitor of the shower, whether it was a gamma ray or a proton?
Yeah, another question is, you mentioned a threshold of something like 500 GeV. And then you hope with 500 GeV threshold, you will be able to measure a lot of gamma ray bursts.
So I believe it was GRB 190114 Charlie. The number is perhaps a little off, but it was detected by magic.
14C, yeah.
Yes, yes, exactly, sir. Up to 1 TeV. And they've since had another very high energy detection that's not quite out yet. As I've come to understand from watching talks at this conference. And so we would be well suited to search for such very high emissions that has been proven and seen in the afterglow phase, as well as theorized in the prompt phase as well.
Well, I think it is a little bit optimistic, I should say, but one should stay optimistic. Concerning this GRB 190114C, the gamma ray flux was attenuated at 1 TeV by 1,000 times. And then I think the main strength of SWAGO type detector or Hawk type detector is time. I think time is working for you day and night, every day. But then I think collection area should play a role. And what is the supposed collection area of SWAGO?
It really depends on the chosen detector, but it would likely be a bit larger than Hawk, which is 20,000 meters squared instrumented, and then with the outrigger array is about, the effective area is about 3 or 4 times bigger, about 10 TeV. So I would expect absolute minimum would be those kinds of values. So
it will be comparable to an IACT instrument, I think. Yeah.
Yes, but we would have the added advantage of we're not limited by slewing time. We're not limited by weather, day or night. And we can look in archival data, so we can perform lookbacks, unlike the IACTs, which have to do the pointed observation follow-ups of satellites, or get very lucky.
It will just limit the redshift of sources that you will be able to see, but certainly I think some sources will be observed. I think GRB sources, I mean, yeah. If they are, especially if they are nearby, I think the chances will be high.
Yes, we're optimistic about it.
Yes. Are there other questions?
Sorry, you cut out for me.
Any other question or no? If there are no other questions, then I think we shall thank Christy for this very clear presentation. Thank you very much. And let's move forward to the next presentation. Yeah? Next presentation, I would like to quote Elisa Bernardini. She is going to talk about the correlation between diffuse gamma ray and neutrino backgrounds.
Good morning, everyone. Thank you very much, Razmik, for your kind invitation to this fantastic event. This is really very successful and certainly very challenging to organize an event. Now I will share my slides. And I hope that you can see them.
Yes, we can clearly see.
Okay. Okay, here we are. Razmik, I can't hear you, so.
No,
okay.
I said we can clearly see your slides.
Okay.
We can see you, so everything looks perfect. Just go ahead. Yeah.
Thank you very much.
I will give you a sign after 15 minutes, about 2 minutes more, and then 3 minutes we reserve for discussion. Yeah?
Okay, thank you very much.
Not too strict, but roughly. Yeah.
Okay, so neutrino astrophysics is a new emerging field which made its first and a most important breakthrough discovery in 2013 with the measurement of a diffuse flux of neutrinos covering a large energy range. So nowadays, this measurement has been confirmed by IceCube through different techniques and different analyses over a broad energy range and also different sky regions. And cosmic neutrinos do show a sizable flux from energies as high as several PeVs and down to few TeVs, 10 TeV roughly, and showing very distinctive properties with respect to the background induced by interactions of cosmic rays in the atmosphere. Now, this discovery is really exciting since it opens up a new observational window onto the universe, but it's also quite impressive. In fact, in the data set collected by IceCube, some of the most energetic particles ever observed are recorded. There is an example here in the bottom right picture with one of the events in the original discovery paper overlaid with the city of Madison. And I think this provides an immediate and quite touchable impression of the sizes and the energies that we are dealing with. Now, this opens up a wealth of new opportunities, in particular, the possibility of observing the universe in regions which are obscured and not accessible otherwise. In fact, because of diffuse radiation fields, both gamma rays and neutrinos do interact, which limits the size of the observable universe to increasingly smaller and smaller distances as we increase the energy, while neutrinos, as also for gravitational waves, we have the possibility to observe the most remote regions of the universe, as this has been shown in this picture. Now, as mentioned, nowadays, the existence of cosmic neutrinos is established through different analyses which are sensitive, for example, to different neutrino flavors, different sky regions, and also a quite diverse energy range. But if we consider the highest energy events, that means the events which have a higher probability of an astrophysical origin, and we inspect the direction of arrival of those events, then there is no emerging sky regions as most likely responsible for those neutrinos. For example, the galactic plane is not outshining in the directions, but also there doesn't seem to be any preferred sky direction, so any preferred astrophysical objects to be responsible for a large fraction of those neutrinos. And the most remarkable aspect is that inspecting the directions altogether, they are quite compatible with the diffuse, with an anisotropic flux, which clearly suggests an extragalactic origin of those neutrinos, at least in the majority of them. Now, on the other hand, we do have experimental evidences of common stories being told by different cosmic messengers. So, for example, 2 of the 3 multi-messenger breakthrough discoveries involve associated neutrinos and photons. For example, with the discovery of the supernova in 1987, associated with the burst of MEV neutrinos, as well as the measurement in 2017 of a high-energy neutrino associated with a gamma-ray blazar in an enhanced state of its emission. Now, since we have experienced tremendous advances in our understanding of astrophysical sources by exploiting electromagnetic data over the broad spectrum with multi-wavelength measurements and studies, we shall certainly expect similar advances and much deeper insights when we combine different messengers. And the discovery of the IceCube event associated with blazars also showed a tremendous boost in the modeling, such that we shall expect important new breakthrough and insights. Now, after the observations of gravitational waves associated with neutrinos, the next awaited multi-messenger discovery shall be the associations of neutrinos with gravitational waves that would open up yet even new and unexplored opportunities. Now, besides the experimental evidences of common stories being told by different messengers, we shall expect a connection out of basic principles. In fact, cosmic accelerators are surrounded by radiation and matter fields in which accelerated particles can interact and give rise to secondaries, in particular photons up to high energies and neutrinos. And for both classes of messengers, we can well reconstruct direction and energy, meaning that we can associate those signals to the original astrophysical objects. and also have insights into the emission mechanism. Now, depending upon the properties of the environment of the cosmic accelerator, namely if it's a field with matter or radiation fields, then different channels can be responsible for the secondaries, in particular proton-proton interactions and proton-photon interactions. Now, regarding the emerging secondaries, in particular for what concerns neutrinos, it happens that the energy spectrum expected in the two different scenarios are relatively and substantially different, meaning that measuring the energy and the energy spectrum can provide us important insights into the emission mechanism. In addition to that, neutrino appear with three distinctive flavors, and some signatures of the emission mechanism is also expected in the flavor compositions and admixtures of neutrinos, meaning that we have an additional fingerprint of what is the underlying phenomena responsible for those secondaries. Now, another multi-messenger important consideration comes when we compare and explore somehow the energy budget, which is contained in the three different messengers. So this picture is showing the energy flux in high energy gamma rays, high energy neutrinos, and ultra high energy cosmic rays. And the first thing which strikes the eye is that the energy flux is comparable, meaning that the energy generation rate of the three different messengers is comparable. So this suggests two important facts. First, that those three messengers seems to be intimately connected, but also that this connection spans over multi-energies, because the energy ranges of the three messengers are also substantially different. Now, combined fit of these three signals have been significantly done and explored in the literature with both scenarios, so proton-rich and photon-rich scenarios. And it's possible to describe this data in both cases. However, the general conclusion which is arising is that while it's relatively simple, or let's say possible to fit in a combined framework the neutrino data at energies larger than 100 TeV, then things are getting complicated and not straightforward for lower energy data below 100 TeV. What happens is that if we consider gamma transparent sources like blazars, then things are really troubled, because the expected associated gamma radiation is strongly outshining the data. And this poses up the quest for hidden sources as at least responsible for a certain contribution to the diffuse neutrino flux. Now, inspecting the neutrino data in more detail, as we have mentioned earlier, different analyses can be performed, sensitive to different flavors, energy regions, as well as sky regions. Altogether, the data is compatible with a simple power law in the energy spectrum with a spectral index of the order of 2.4. There is widely discussed a mild tension between different subsets of the data, a tension at the statistical level of 1 sigma, because indeed the data is affected by large errors, especially at the high energies where statistics is limited. Now, different analyses have been performed fitting this data with more elaborated spectral shapes motivated by specific astrophysical models for the sources or the putative sources. But the conclusion which can be derived at this point is that some of these models do describe the data, some do not describe the data at all. But altogether, there doesn't seem to be a model which is describing this data better than a simple power law, because of the statistical power that we have at the moment. Now, by allowing more background and increasing the collection area, it is possible to test the hypothesis of given preferred sky directions as outshining or responsible for an important fraction of the astrophysical neutrinos. And this using techniques inherited from astronomy. But the state of the art in this approach at the moment is that there is no single spot in the sky which clearly outshines. And the reason is related to the huge trial factors which have to be paid, which penalize the analysis when we treat all sky pixel equivalently, because the number of sky pixels being explored is huge. And a way out to solve this problem is to make well-educated hypotheses of which the preferred sky direction shall be, and then limiting the statistical tests on those hypotheses only. Of course, for this approach to work, the educated hypothesis has to be hopefully the right one, and the number of hypotheses to be tested has to be limited in order to limit the trial factors. Now, based on multi-wavelength data, it is possible to compile educated catalogs for the best bet for neutrino emitters. And so far, one of the best indicators for possible neutrino counterparts has been considered the luminosity in high energy and very high energy gamma rays. Now, these catalogs have been tested, and what happens is that one sky region in the IceCube dataset, which is emerging in the Northern Hemisphere, so the hottest spot in the Northern Hemisphere, is especially coincident with the location of a cataloged source, which is NGC 1068, which is a starburst galaxy. Now, for this one source, there is also long exposure gamma ray observations, including even Cherenkov telescopes. And if this signal, which is emerging, is due to the neutrino, then this is a very intriguing object because it's much more luminous in neutrinos than in gamma rays. And this is now, let's say, stimulating new theoretical developments in interpreting this source class. But from the neutrino point of view, what can be said is that this source, together with other three ones, including the Blazar TXS 0506 and other two BLX, are emerging from the statistical tests at a level of 3 sigma after trials. And these sources are also collectively inconsistent with background at a post-trial significance of 3.3 sigma. So at this point, they can be still compatible with background fluctuations because we are below the golden 5 sigma threshold. But it should also be said that if individual sources are to stick out, then they shall definitely be among the samples of the excesses that are emerging. Now, it is also possible to test diffuse regions in the sky as responsible for neutrinos. And the best bet for an extended diffuse region in the sky is the galactic plane, because we know that cosmic ray interactions with the surrounding matter and radiation fields are responsible for the diffuse radiation being measured in great detail by gamma ray satellites. And an associated expected neutrino signal can be robustly predicted, constructing templates of the space distribution as well as the energy spectrum. These templates are, of course, model dependent, so they can be, let's say, questionable in the fine details, but performing a maximum likelihood analysis shall emerge a certain neutrino excess if the hypothesis of cosmic ray interactions holds. Now, recently, a combined analysis of IceCube and Antares data has been performed, trying to verify if there is an excess of events compatible with the galactic plane, with the likelihood analysis, and no excess has been found. And this allows to constrain what's the maximum allowed contribution of neutrinos from the galactic plane to the overall diffuse neutrino flux, which is being measured. And this limit is of the order of less than 10%. Now, what else can be said? Now, we discussed already the discovery of a neutrino associated with the gamma ray blazar. And this is a very exciting and interesting case, which has boosted tremendously also the development of theoretical models. But there is one aspect which is certainly intriguing and emerging. And in particular, the fact that IceCube archival data has also highlighted an earlier lower energy flare in 2014 to 2015, which happened during a gamma dark period in the source emission. So this suggests altogether that neutrino emissions sometimes seems to correlate with gamma ray emission, which can extend up to very high energies, as the MAGIC telescope has discovered in 2017. but sometimes does not seem to correlate with gamma ray emission. So altogether, certainly gamma ray blazars, if responsible for neutrinos, don't really behave as straightforward, simple one-zone blazars as has been modeled up to now. So more complex models in terms of geometry are needed, and also the phenomenology might not be so straightforward. Now, it is possible to provide constraints on the overall contributions of gamma ray blazars to the diffuse flux measured in neutrinos. And this has been performed with a combined analysis using the Fermi-Lat blazar catalogs and using large data sets of IceCube data, and performing essentially a stacking analysis on preferred gamma ray blazars directions. So no overall excess of neutrinos has been clearly identified, and a constraints on what is the possible uppermost contributions of gamma ray blazars to the diffuse neutrino flux has been derived, which is at the level of 30%. So what we can conclude is that gamma ray blazars don't seem to dominate the diffuse flux as measured by IceCube. Now, this, together with what we earlier said regarding lower energy neutrinos, poses the quest for other source populations to be investigated. Now, transients are particularly appealing because, thanks to the timing informations, they would allow additional constraints, additional reductions of the backgrounds. And among transients, very interesting cases are, for example, failed gamma ray bursts, in which a supernova is exploding, but jets are choked, or supernova exploding in dense circumstellar medium, which then behave as supernova remnants on much compressed timescales. And finally, also tidal disruption events, which is a new class of events emerging, in which a star orbiting around a supermassive black hole is orbiting too close and is essentially torn apart by tidal forces. And then the debris are accelerated and accreting, launching the possible generation of jets. Now, one high energy neutrinos from IceCube has been recorded in coincidence with one such class of events, with the neutrino arrival time around 150, 170 days after the estimated time of the event. And a late activity associated with the central engine is also suggested by the radio data. Now, from the statistical point of view, the chance coincidence for this one event is estimated to be at the level of 0.5%. But then a second possible candidate has been observed on a coincidence timescale of the order of a year. And therefore, it's interesting to estimate from the theoretical point of view what the contribution of this class of events could be on the diffuse neutrino fluxes. And at the moment, estimates are at the level of percent level for this class of events itself. So this is a possibly new emerging source class, but doesn't seem to be also the main contributor to the diffuse flux observed in neutrinos. Then something else can be said regarding other wavelengths. For example, two of the highest energy neutrinos recorded by IceCube happen in periods of enhanced radioactivity, which however evolves on relatively long timescales of the order of years. This is the case, for example, for the Texas source, so TXS0506, but it's also the case for another blazars, PKS1502. So in both cases, we have bright radio emission at the time of arrival of neutrinos on timescales of many months. So recently, an analysis has been carried out investigating if radio HE1s are coincident with the highest energy neutrinos collected by IceCube. So a sample of historical IceCube alerts has been analyzed against the VLBI and RATAN data. And what this analysis suggests is two considerations. First, as shown in this plot in the bottom right, HE1s, which are spatially coincident with high energy neutrinos, seem on average brighter in radio than non-correlating ones. And also the neutrinos seem to happen during bright flares on time scale of half a year to a year. So this opens up the possibility that other tracers shall also be considered or can be considered or shall be considered as possible indicators for likely neutrino emission. So this brings me to the conclusions. What shall be said is that an important galactic component to the diffuse neutrino flux at energies larger than 10 TeV is currently disfavored. And this is based upon our understanding and our knowledge based upon gamma ray data. So correlations or indirect correlations between neutrino and gamma ray data. But more has to happen. First of all, we do have indications and the first measurements of diffuse gamma ray backgrounds at much higher energies from Tibet. And recently we have also the exciting results from LASO. So in the future, understanding what's the hadronic fractions to those signals is of uppermost importance to understand what the galactic contributions of neutrinos can be to the diffuse flux which is being measured. And also new instruments are appearing, are awaited and being built, which are complementary to IceCube, especially on the field of view and therefore on the sensitivity to the galactic component. Now, bright jetted extragalactic sources like blazars, but same considerations are actually driven also for gamma ray bursts, which I haven't discussed today, don't seem to dominate the diffuse neutrino fluxes. They can't be the most important players, or they can't explain the overall flux altogether which is being observed. So the question is being asked whether we are testing the right sources. On the other hand, other new source classes which are emerging don't seem to be more favorable concert masters. For example, I discussed tidal disruption events, which don't seem to be even more important contributors. So most likely several populations are indeed playing a role. More wavelengths are still to be explored, especially using large coverage and large monitoring data sets. And in this respect, radio seems promising. So now it's very exciting to also in this case to have an estimate of what can be the maximum contributions. And this is certainly coming next. But meanwhile, the real-time programs, so the follow-up at multi-wavelengths of neutrino alerts are delivering a set of very interesting and exciting possibilities. And rather different best bets, which is questing for more multi-messenger data and more multi-wavelength data in association to neutrino to help solving this mystery. So thank you very much, and sorry for taking time.
Thank you very much, Elisa, for this very interesting presentation. I myself have a question. If others want to ask question, Elisa, please prepare your question. My question is about one slide where you were comparing diffuse gamma rays, neutrinos, and then cosmic rays at very high energies. There was a very interesting plot. This one. So I think I find that it's a very interesting plot because it shows the spectral energy distribution for these three very different components, and they seem to be on a similar level, not the same, but similar level. But when I go to the right on the plot, the energy is becoming much higher, which means that the number of events is much less. So what does it mean much less? It means that we should try to find much rare things, much less, right? So if I go 1,000 times higher or 10,000 times higher, spectral energy distribution is the same. This tells me that this event is 10,000 times more rare, yeah? I would interpret so. So then this tells immediately the direction where things should develop, yeah? Collection area, so very simply, yeah? Because 10,000 times, yeah.
Yes, and also the energy coverage, because of course there are also important gaps in between the data coverage. And, you know, this is very striking because, you know, the energy generation rate is the same. So this is what this plot is telling us. And this is, it can't be really by chance coincidence on these very different messengers and also very different energy ranges. But somehow the devil is in the details. For example, it can't also be that those neutrinos are associated right away to those cosmic rays because we don't have the proper energy proportions. So we know that, you know, in the modeling of the interactions, then we shall have a 20th of the proton energy for example, if neutrinos are produced by proton-photon interactions and so on and so forth. So indeed, those neutrinos shall come by some fraction of the lower energy cosmic rays, but somehow the mechanism that is responsible for those particles is capable of injecting the same energy rate. This is definitely to be disclosed. But then you're right. Somehow the quest for ultra energy cosmic rays is important per se. It's a field which is extremely challenging but exciting at the same time, and there is an important pressure in this area. But even in the context of multi-messenger associations, this is definitely an important ingredient. Especially, it's also the region where we do have to expect associated neutrinos, but is also posing the quest for facilities exploring these very rare statistics at high energies in neutrinos as well, because we are not yet sensitive to, for example, the neutrinos due to interactions of ultra energy cosmic rays with cosmic microwave background. So this is definitely pushing for new facilities at the uppermost energies.
Yeah, thank you very much, Elisa. Is there any other question? One last very short question. What about the GVD? I think GVD will start entering into game at really very high energies, right?
Yes, so I don't know if I have, sorry, maybe do I have a slide? Oh.
10 to the 16 or higher, so is my impression, right?
Yes, so here we have Lake Baikal, and the new facilities are under construction. So actually, there is quite important progress coming there, and there are also candidates at uppermost energies being reported by Baikal. So this is also progressing very fast, and the advent of the new facilities is certainly in the nearest future. Also, an important and impressive progress is being achieved in the Mediterranean, with strings being deployed. So altogether, we shall expect exciting new players coming, which in particular will be interesting because they have an important complementarity, mostly in the field of view, but not only. So this is certainly an important new piece of information which shall come in the near future. And also there is, of course, the project of extension of IceCube of a factor 10 in effective area, particularly at high energies, but this is in a bit longer time scale to come.
Thank you very much, Elisa. I do not see any other questions. I would like to thank you once more again for this very interesting presentation. And then we go forward, and the next presenter is Christian Frug, who is going to talk about insight into the galactic center environment from VHE gamma ray observations with ground-based facilities. Christian, I would like to invite you.
Yes, thanks, Rasmik, for introducing me and for the opportunity to give this presentation. I hope you can hear me well and now also see my screen. Yes, so the galactic center, well, we've seen this. This topic has been awarded a Nobel Prize very recently, and it's definitely a very complex topic. It involves a lot of scales, a lot of different instruments for studying it, and it's a big and complex puzzle. You've seen in the last presentation that already basically deciphering blazars is already challenging, or is challenging, and we have a similar object in our own galaxy. So you would think it's much closer, but it's nevertheless equally challenging to really tell what is linked to what. There are instruments that can, well, are on the verge of even resolving the central black hole at the galactic center. And if you compare this to very high energy gamma ray observations, then you will see that you can by far not reach this level of resolution. But nevertheless, I try to motivate for you that very high energy gamma ray observations might be a very important piece in the puzzle of understanding this environment. And therefore, I will start with a short, very shallow overview of the scales involved in this puzzle, and then I will switch to gamma ray observations. So let me switch to the first slide. Yes, this is a very rough, just motivation of scales within 3 slides. So this is just an optical image of our galaxy. You have very different environments astrophysically in the disk, which is around 30 kiloparsec in diameter and only 0.3 kiloparsec high. There you have young stars, gas, molecular clouds, dust. Things are happening there. And then if you move closer to the center, you have this central bar, which seems to be a bit more boring. So you think maybe that towards the galactic center is just boring, old stars, low star formation rate. But then you have in the very center only the central, very few degrees, the central molecular zone, only 250 parsecs in diameter. And there you have again very dense molecular clouds and quite high star formation rate, and also a lot happening in high energies in radio, X-ray, and we'll see this. And now just to continue this feeling for scales here, if you just imagine that this red box from the past slide is actually here. This radio image of the central molecular zone, where you have a lot of these shells from supernova remnants, and you have also other structures in radio, like this galactic center arc radio structure. And if you zoom in even more, so here we're down to 70 parsec, you have this structure. It's a supernova remnant, Sagittarius A East, which is already very small in size compared to other structures there. And then if you would zoom in even more here, this closest zoom in would be the tracks of the stars, the closest stars to the central black hole in our galaxy. And this would then be only 0.05 parsec in diameter. And of course, the observation of those stellar orbits is what finally led to the discovery of this central black hole of our galaxy named Sagittarius A star. And this whole topic has received the Nobel Prize this year. And well, this object is of course not only visible. It's not a total it's not a ghost, so it's not invisible completely. It's not only visible by the tracks of other objects around it, but it also seems to be linked to a point-like object that's seen in radio and in X-ray and in infrared, which directly brings me to, so maybe one thing to mention is that, of course, there's now a very big campaign ongoing, namely the Event Horizon telescope, that is now attempting to spatially resolve the event horizon of this black hole, which is on the order of 10 microarc seconds in angular diameter. And this brings me to time scales involved there, because also here you have a wide variety of scales. We start here again with the central point source, which shows a minute-to-day scale variability in X-ray, infrared, and radio. The brightness of the object in various wavebands can change by orders of magnitude in this very short time scale. And the emission must, of course, by time scale alone, it must come from the direct vicinity of the black hole, the event horizon. And so far, it has, at least to my knowledge, not really been possible to link this to any specific events, for example, stars or like this gas cloud that I will talk about later again, something that came close to the black hole, something that could have disturbed the accretion flow. It was not really possible to find this link from things that happen further out to things that happen very close to the black hole. And that's one of these big open questions around the galactic center. Then if we go in time scales, and of course this involves then also again spatial scales, we go out again, we go to intermediate scale variability. There I picked one example, which are those X-ray echoes that have been observed using Chandra, I think, where so it's interpreted as an echo of an X-ray flare emitted by Sagittarius A star, and the echo in the surrounding molecular clouds can be seen moving or changing its shape and moving outward in the time scale of years. So this is definitely a link to something happening close to Sagittarius A star. And the time scale, I said, here is years. And again, here the cause is not precisely known because, as I said, up to now, there is no real link between those phases of activity and the real causes for those flares, neither on those timescales nor on longer timescales. And then last but not least, for this introduction, we also have, well, again, we move out spatially, but also in terms of timescales, of course, there have been large-scale structures discovered in X-rays and gamma rays. So first, to mention those Fermi bubbles that were discovered in 2010. So those are really galaxy-scale structures, basically huge lobes that emit gamma radiation. This could be linked to past activity of Sagittarius A stars, so something like a jet or some outflows. But it could also have completely different explanations, like just an epoch of intense star formation. Also, very recently, similar bubbles have been discovered by Erosita, basically mimicking the size and shape of the Fermi bubbles, even larger in scale. The time scale here is on the order of millions of years. So it's really hard to tell what happened back then and caused those bubbles, but it could of course be linked to the central object. Now, as I said, I want to discuss very high energy gamma ray observations. Therefore, I wanted to start with a very shallow and very quick introduction to another instrument, Fermi, which has well, a lower energy threshold. It is much smaller in collection area. And you already heard about the Fermi bubbles. And you might ask yourself, why not talk about this more in terms of the galactic center? And just to motivate this, I picked some count maps that I did myself some time ago. So this is maybe not the most recent amount of data that has been collected by Fermi, but just to give you a feeling of how difficult it is in terms of low resolution, low spatial resolution, and also a number of events that you can detect with Fermi. So it's really difficult in this crowded field of view to do proper source association. And therefore, for this very crowded field of view, it's actually imaging air Cherenkov telescopes that are a very good choice to trying to study this region. And here, well, I know that we all are probably aware of this technique, so I won't go into detail, just show the most important facilities. This is Veritas in America. Then in the Canary Islands, there's MAGIC on La Palma, and there are the HESS telescopes in Namibia. Those are the most important facilities operating with this very indirect observation method of imaging air Cherenkov observations. And now coming back to the scope. So what is it, what you can actually resolve, and what's actually visible for IACTs? You can definitely not go to the very large scales because of the limited field of view, usually of the order of 1 or 2 degrees of those instruments. And you can definitely also not resolve very small structures in the arc-second regime. So what we see, if we talk about the galactic center and about ICTs, is actually the central molecular zone. So a region that extends roughly 200 parsec in width and around 100 parsec in width, in height. And this is a very rich astrophysical environment. You see here, there's this composite image of radio and millimeter and infrared radiation that highlights different astrophysical sources of electromagnetic radiation, supernova remnants here, mostly seen in radio, and also those large-scale structures in the galactic center. Then you have dust seen mostly in millimeter radiation, and then also stars in infrared. There's of course a high risk of source confusion similar to Fermi, but since the resolution is slightly better with Cherenkov telescopes, you get a chance to resolve things. And the Basically, the story started roughly 20 years ago at the beginning of the new millennium. The first detections were made with imaging Cherenkov telescopes. The very first reports came from Kangaroo 2, but they reported a detection, but the exact spectral and spatial properties were later not really confirmed by other observations. Like, for example, here, the first detection with the Whipple telescopes, also 2004. Actually, everything went very fast at the time. Also, HESS then showed the detection of a source, HESS J1745-29 in 2004. And then 2 years later, also MAGIC presented the first detection of the object. Here you see that there's not, you just have a point source, what seems like a point source. Maybe there is some extension, but then things progressed relatively quickly. Just keep in mind that those are still the same instruments, but data analysis methods have vastly improved. And the next big wave of important findings came from HESS between the years 2006 and 2010. So they first of all reported extended very high energy emission, so-called galactic ridge that you can see down here. So by subtracting a point source here and also this supernova remnant or pulsar wind nebula over here, you see that there is some residual emission along the galactic plane that sticks out, and then it's most, well, there's hardly another explanation, and this to be cosmic rays interacting with the dense molecular clouds in that region. So it's hadronic emission. Then also a few years later has showed that the central point source here is Sagittarius A star, or which can be associated with Sagittarius A star, shows a cutoff at roughly 10 TeV. And also they've shown that they can precisely locate the position of the point source and exclude other source candidates, like, for example, Sagittarius A East, the supernova remnant, as a potential source for the emission, and drawing the attention closer to the black hole. Then starting in 2012, also MAGIC started a quite intense observational campaign. This was all triggered by a gas cloud-like object that was seen on a very steep, very eccentric trajectory or orbit towards the galactic center black hole. And the pericenter passage was predicted for this time period between 2013 and 14. And therefore a monitoring campaign started. The MAGIC recorded and published light curves, which can be seen here. But up to now, no variability has been found, neither in the lower energy band, larger 1 TeV, nor in the higher energies. And as you will see in my last slide, actually also Veritas recently published new light curves, extending this even further, and also didn't find any hint for variability. And then in 2016, it was again HESS that published important new findings about this diffuse component. So this what was called back at the time the galactic center ridge emission. So this time they also published a spectrum of this emission, where they counted photons from those circle-like regions, and also this what they call a Pac-Man region. They did two things. So first of all, they published an energy spectrum that seems to indicate no cutoff below 100 TeV, and leads led them to claim that there is a potential pevatron located very close to the galactic center. And this gets further supported also by what they find in terms of the needed flux density to explain the gamma ray emission from those regions. You can calculate how much flux density of cosmic rays is required, and you see a 1/r decay that peaks at the location of Sagittarius A star, and this favors an outward diffusion scenario of cosmic rays from that region, and of course hints at a link to the galactic center black hole. Then also similar studies have been conducted with MAGIC in the following years. Here you can see a MAGIC sky map, now also above 1 TeV in energy. You also see this emission from the galactic center ridge. The analysis method that was used by MAGIC is a bit different. An approach was chosen very similar to the Fermi data analysis pipeline, where a spatial likelihood fit is used in order to get or overcome this problem of source confusion. So the MAGIC analysis uses these 3 point like sources, G09, the Passover Nebula, this a point-like source here at the location of the galactic center arc, and the point source for Sagittarius A star, and then models the diffuse emission by the CS radio emission contours, or by this CS radio emission intensity map. This can also then be used to extract SEDs of those different components. Blue here is the diffuse component. And it can also be used if you cut the CS emission map into rings and then fit them in a single bin in energy, but you fit them separately spatially, then you also end up with a similar increasing towards the galactic center point source profile for the emission, basically, more or less confirming the finding of Hess. Here, also a later publication of Hess has extracted a similar spectrum of the diffuse emission in the galactic center. Those are the orange data points here, where they extracted events from a slightly larger area, which is here indicated with this orange box, in comparison to the Pac-Man region, where the events come from that led to those green data points. And the MAGIC results from fitting the CS map as a model for the diffuse emission are compared here. And while there is not really a hint for a cutoff, or even a hint for continuing emission up to 100 TeV in the green data points from 2016, you can see that there is at least a hint of a turnover in the emission that's collected from the larger area. And looking at MAGIC data alone, a 2 sigma hint could be found for a cutoff at around 20 TeV, which is of course not yet fully conclusive. And this already brings me to my final slide of the news from various instruments. And this is a very recent study published this year by Veritas, where they again also revisit the region and also use similar methods that have been already applied by MAGIC and Hess. For example, they use the same circular regions for extracting their flux for the diffuse emission that they measure, of which they also produce an SED, the blue data points here. And the SED of Veritas seems to not really show a hint for a turnover here, but also of course the statistical errors are relatively large, probably also due to the fact that the extraction regions are relatively small if you compare it to the large extraction regions that went into Hess 2018 or MAGIC 2020. They also show a sky map above energies of 10 TeV, where you, for example, see that a lot of source components, or for example, this source components G09 disappears, while here in this arc region, they show quite strong emissions still, and they even model this with 2 separate sources in this location. And last but not least, they also show a very long light curve over the time scale of 8 years in 3 different bands of energy, above 2 TeV in blue, and also daily light curve. Sorry, it's actually a daily light curve also over 2 TeV, and then 1 over 5 TeV. But the bottom line is that they don't see any long-term trend over nearly 1 decade of observations. And this brings me to my conclusions. So the galactic center has been studied quite extensively with very high energy gamma ray instruments over the past 2 decades. And if you just look at what happened in terms of progress in this time, it's really astonishing, from just a mere detection to really very detailed studies. There is the central point-like source, which could be consistent with Sagittarius A star and the supermassive black hole. On the other hand, there's no variability that could be detected. So it's hard to bring those 2 into connection via any variability. So the point-like radio source and the gamma ray point source. But there is this degree scale extended gamma ray emission that is spatially consistent with the massive molecular clouds. And this has an energy spectrum that reaches several tens of TeV. And there's no clear cutoff or no clear indication for a cutoff. And this strongly hints at cosmic ray acceleration that could reach up to roughly PeV energies. And also the morphology suggests that the source for those cosmic rays must lie very close to the black hole. So the question remains, is Sagittarius A star the main cosmic ray accelerator? Is there any link to past variability of Sagittarius A star? And is there maybe even some link to the Fermi and Rosetta bubbles? So those are the questions that are still unanswered. But there is definitely this exciting period will continue, because we are now expecting results from water Cherenkov arrays. I put here Hawk and Lasso. I know it's challenging for those two, but we just heard also about SWGO that might maybe finally give us a very nice view also from those instruments, those types of instruments on the galactic center. And that's it. Thanks for attention.
Thank you very much, Christian, for this comprehensive presentation. I think it gives a very good impression about all these studies. Before people may decide if they want to ask a question, I have one question. So you showed a picture where you were fitting the annulus around the galactic center, and then from this annulus you were deciding about the diffuse emission strength on different distances from the center. But looking to this picture, which is shown in color, and color may be somewhat misleading, what if the annulus on the link on the left and on the right, they show very different results, maybe? So, and you show the average. Do you think it may have some effect, or?
So this is something that has been looked into by MAGIC, and the problem is twofold. So the first problem is, of course, that the emission is much brighter on the left side than on the right side, but also the strength of CS emission, and therefore the probable density of giant molecular clouds is much stronger on the left side. And then from the weak gamma radiation on this side, you have very, very weak statistical significance. So it's hard to tell if maybe also the cosmic ray diffusion is asymmetric or not. And in addition, the second problem is that also the CS emission as a tracer for dense material might not be such a good tracer anymore if you go to less dense environments. So maybe in this environment, the CS emission strength is not perfectly proportional anymore to the density of material. Maybe you would need to take into account also CO emission or traces for less dense molecular clouds. So it's definitely an interesting question, but it's hard to answer with the data at the current stage.
Yeah. Yes, I think you answered already in part. At least I understand better now. But then I think it undermines one other claim. So you did mention that the gas density on the left on this picture is higher than on the right, right? But then I would estimate that this plays a role in the diffusion. So I would then anticipate that the diffusion on the left happens somewhat different from the diffusion on the right, and then this will change the bias a little bit more, right? You cannot say it's the same diffusion left and right.
That's probably true or very likely. The problem is just that in gamma rays, we lack the sensitivity for this region on the right to really tell if the diffusion happens differently. If there is maybe, for example, it's more 1/r on this side, and maybe it's more linear propagation, and therefore 1/r.8 or even 2 on the right side. But maybe with more data, maybe from CTA also, this can be answered.
Well, I think we shall not go that far in future. Maybe we shall try to do something with available data, because this is an interesting claim. If diffusion happens to the left and to the right with different speed and different way, different exponent. This carries information, definitely. And for the time being, we have a symmetric picture. I think maybe one next step should be made to go away from the symmetric picture and to see if the asymmetries are really there, and if they are there, go for explanation. You already offered the explanation, but it's a very interesting question.
Yes, definitely. Maybe it will take a joint analysis of multi-instruments, multiple instruments.
Why not? Why not? Is there any other question from participants? I do not see a question, so I would like to thank you very much for this very interesting talk, Christian.
Thank you.
And then I would like to ask for the next presenter. And the next presenter is Giacomo D'Amico. And Giacomo is going to talk about a very interesting topic. He's going to talk about probing the Lorentz invariance violation by using the MAGIC telescope data.
Hi, thanks. Can you hear me?
Yes, we can very clearly hear you. We can see you. We can see your slides.
Oh, perfect. So thanks, Razmi, for the introduction and also for the invitation. And today, as Razmi said, I'm going to talk about the recent results on the Lorentz invariance violation study using the MAGIC telescope from the observation of GRB 190140C. A study that we did in collaboration with the following authors on behalf of the MAGIC collaboration. So I think we are all familiar with imaging atmospheric Cherenkov telescope, but let me briefly introduce these telescopes. So that their basic the way they work is that they use the Earth atmosphere as a calorimeter, and when charged particles traveling faster than the speed of light in the atmosphere produce Cherenkov light, and they are ultimately recorded by this telescope. You can see here on how this Cherenkov light looks like in the camera of this telescope. Charged particles that are produced by primary gamma rays or cosmic rays interacting in the atmosphere. Here you can see instead in this beautiful picture the two MAGIC telescope located in the Canary Island of La Palma, and the energy range that they can cover goes from 300 gigaelectron volt above 15 teraelectron volt. But now let's move on instead of this guy here, the very famous GRB 190140C. You can see on the left the paper that the MAGIC collaboration published on Nature about this unique observation. On the night of January 14, 2019, MAGIC detected the most energetic photons ever observed from a gamma ray burst, with an energy that ranges from 300 gigaelectron volt to 2 teraelectron volt. The observation started about 62 seconds after the GBM trigger time, here indicated as T0. And the observation lasted for about 20 minutes, during which MAGIC were able to observe, after selection cuts, 729 events, where I explicitly say events and not gamma rays, because we know from on and off observation that approximately 40 of them are background events. So events that are produced not by gamma rays, but by cosmic rays. Here instead, I want to show you some basic properties, intrinsic properties of this gamma ray burst, so that are going to be very important for our analysis. So on the left, you can see the temporal evolution. Here you can see the point, the light year point obtained by different instruments. The one that we are interested in are the green points that are obtained by MAGIC in the energy range that goes from 300 gigaelectron volt to 1 teraelectron volt. As you can see here, as I said before, we unfortunately miss the first 62 seconds of this GRB. essentially we miss the prompt phase of this gamma ray burst. So we need to perform some extrapolation on these first seconds of observation, extrapolation that are based on theoretical models. And if you want to know more detail about this kind of about that, you can check, for instance, Alessio Berti and Davide Micheli's talk on this conference. Although I think that their talk took place yesterday, so if you miss it, you can still download the slides in this parallel session, or you can see the two papers published by the Magic Collaboration on Nature. Another important thing that needs to be considered during this talk that you need to remember is that, as you can see, the light curve observed by MAGIC is very well described by a power law distribution with an index of -1.5. Regarding instead the spectrum, this is also very well described by a power law with a spectral index of 2.5. Spectral index that is assumed to be time independent, assumption that is justified by the observation. So what we want to do with this gamma ray burst? We want to detect the so-called Lorentz invariance violation effects. There are different ways in which this violation of the Lorentz invariance can be manifest in astrophysical observation. For instance, Christine in the very first talk briefly mentioned about the possibility that Lorentz invariant violation can produce a cutoff in the flux. But here instead we are focusing instead on another kind of effect produced by Lorentz invariant violation, which is a time delay in the arrival time of this photon of these high energy photons. Time delay, which is predicted to be by these quantum gravity models to be given by this expression, where E is the energy of the photon, EQG instead the quantum gravity energy scale at which you should expect to observe this kind of effect. And this quantum gravity energy scale is expected to be very close to the Planck energy. D is instead the distance that these photons have to travel, in which the fact that our universe is expanding is also taken into account. And S instead is a model parameter that can take values +1 and -1 respectively for the subluminal and superluminal case. Now, if you take into account the redshift of this gamma ray burst, which is of 0.42, and we take the usual cosmological parameters, we get that for the linear and quadratic case, we have the following expression for the time delay that we should observe from the gamma rays of this gamma ray burst, where eta is defined as the ratio between the Planck energy and the quantum gravity energy scale. Well, for the quadratic case, we also introduce this factor here, 10 to the -16, just to have a proportionality which is of the order of 1. I want to bring to your attention the following fact, that here we are trying to detect an effect that is suppressed by the huge Planck energy. But nevertheless, because these photons, because of the energy of these photons and because of the huge distance that these photons have to travel before reaching our detector, in this case, the MAGIC telescope, this effect is of the order of 10 or 20 seconds, which is quite remarkable if you think about it, because this effect is suppressed by the Planck energy. And but how we can hope to detect this kind of effect in this gamma ray burst? So first of all, we need to take into account. Oh, I cannot go to the next slide. Okay. First of all, we need to take into account the instrument response function of the MAGIC telescope, which means that we need to take into account the effective area, which is given here in this plot, and the energy resolution of the MAGIC telescope. And we need also to take into account the ABL attenuation, essentially what we need to build is the probability distribution function of detecting a given gamma rays with a given time of arrival and estimated energy. I want to show you in the next slide how this probability distribution function looks like for the linear case in time. Here I am assuming eta equal -7, so it means that we are in the superluminal scenario, and the quantum gravity energy scale is 7 times smaller than the Planck energy scale. And here the axes are in logarithm scale, and the x-axis started at 62 seconds after the GBM trigger time. So when MAGIC start observing this GRB, as you can see, as expected, the more we go in energy, higher in energy, the more this time distribution is deformed. Here in blue, we have the time distribution for a gamma ray with the estimated energy of 2 tera-electron volt, which is the highest energy observed in our data set. While instead in red, we have the time distribution for a gamma rays of with estimated energy of 300 giga-electron volt. And as we start increasing the value of eta, so it means as we start approaching the null hypothesis, in which there is no quantum gravity energy effect. I don't know why the slides don't move as expected. There is a delay in the way I press the button and the slides move forward. Okay, anyway, as I start increasing the value of eta that you can see here on the right, the deformation becomes smaller and smaller. As we reach the null hypothesis, okay, I managed to reach the null hypothesis. Okay, now it's working. As I reach the null hypothesis in which there is no deformation induced these Lorentz invariance violation effects. But if I start increasing again the value of eta, which means that if I start entering the subluminal scenario in which high energy photons travel slower than the speed of light, you can see here that the peak on the left that we should be able to observe in the first 62 seconds of this gamma ray burst, but that we unfortunately miss, start entering the MAGIC time window of observation. So already here, just by looking to this plot, we can see that we can exclude value of eta that are equal or bigger than 5. This is because if eta had been equal to 5, we wouldn't be able to observe tera-electron volt gamma rays in the first seconds of observation of this gamma ray burst, which is indeed not the case, because actually MAGIC detects in the first seconds of observation tera-electron volt events. And according to Lorentz, to this Lorentz invariance violation effects, this should not be possible, because these high energy photons would have in their time of arrival a time delay. So how do we quantify this kind of what we just saw in the previous slides? In order to do that, we built a likelihood profile. Here you can see on the left, on the right, the likelihood profile as a function of the parameter eta for the linear and quadratic case, where the blue and red line are 95 lower and upper limits threshold that are obtained from Monte Carlo simulation. And the value that better describes the observation is eta equal -0.6 for the linear case, and eta equal -0.3 for the quadratic case. And also here you can see that from this likelihood profile that the null hypothesis here with this shown here with this vertical line is still compatible with observation. But there is one thing that till now we ignore. The thing that we ignore is the following. is our intrinsic model actually compatible with the null hypothesis? In order to test this assumption, what we did is that we generate Monte Carlo dataset by reshuffling and bootstrapping the real dataset, so that any quantum gravity effect, if present in our observation, is destroyed, but the temporal and energy distribution are preserved. And when we perform this Monte Carlo simulation, we essentially redo the same analysis that we did for the real dataset. And as you can see here, here in this distribution, we have the value that, of eta that better describe this Monte Carlo, this fake dataset. And you can see that actually we have a bias in our analysis towards negative value of this value of eta. And this also shows that our data are very compatible with the null hypothesis. So by taking into account this bias and by taking into account the likelihood profile that I showed you before, we are then able to put the following 95 lower limits on the quantum gravity energy scale. So you can see here in this table, the quantum gravity limit for the linear case. So we have 0.5 and 0.58, 10 to the 19 gigaelectron volt. So our lower limit are very close to the Planck energy, which is 1.2 10 to the 19 gigaelectron volt. And as I said before, this is again quite remarkable, because here we're trying to prove effects that are suppressed by the Planck energy, but nevertheless we are able to probe these huge energy scales that wouldn't be impossible in other experiment. When instead for the quadratic case, the limit that we put are 5.6 and 6.3, 10 to the 10 gigaelectron volt for the superluminal subluminal scenario respectively. In this table instead, I want to show you a comparison with previous limit obtained by different analysis. So you can see on the left we have the source that has been used in the analysis. Here we have the redshift, and instead in this table we have the type of source that is being used. And in these two columns we have the quantum gravity energy scale for the linear and quadratic case, that is the lower limit that has been put by this analysis. And as you can see here, the values that we got from this unique observation are not the most stringent one that was put. For the one that were done from the analysis of this other GRB observed instead by Fermi are more stringent. This is not surprises, because even though our photons are the most energetic photons ever observed from a gamma ray burst, our analysis was limited by the fact that the light curve that we observed, that I showed you before with the green line, is featureless. Essentially, it's simply described by a power law distribution, and there is no variability in this distribution. And this limited the sensitivity of our analysis. So just to summarize, we observe gamma rays from 300 gigaelectron volt to 2 teraelectron volt. And we use this unique data set to perform a likelihood analysis, making a set of conservative assumption. We assume an intrinsic likelihood that is derived from data and from theoretical models. We assume a smooth power law independent from time. And our quantum gravity effects were described by a model parameter eta, that is the ratio between the Planck energy and the quantum gravity energy scale. And the value of eta that we obtain for the linear quadratic case are very much compatible at 1 sigma with the null hypothesis of no quantum gravity effect. And then with this likelihood analysis, we derive the following 95% confidence lower limit for the quantum gravity energy scale. So thank you for your attention, and let's hope in the future to be able to observe a gamma ray burst in its prompt phase, so that we can boost the sensitivity of this kind of analysis.
Thank you very much, Giacomo, for the very interesting talk. One question to you. I think, meanwhile, people may think if they want to ask other questions. So Very recently, LASO collaboration has put in AstroPH a paper on a quantum gravity limit, a very stringent limit from their data. And they measured peta electron up to peta electron volt energies. Yeah. So I think from Crab Nebula it was maybe 800 tera electron volt, but there was one source where they measured above 1 peta electron volt. So can you somehow comment on this, because what LASO collaboration did, and this is different type of approach to quantum gravity problems, and just somehow to give us an impression what is what.
No, yeah, it's different because I said before, what LASO did in its study was to look for quantum gravity effects that are not of this kind of a time delay effect, but they're looking for a cutoff. They cannot do a time delay because in order to do a time delay study, you need a transient source. So that's why gamma ray bursts are very much suited for this kind of study, because you need a transient source and you need a kind of variability in your data set in order to perform this time of flight analysis. So their analysis is different because instead they were looking for a cutoff effect. And according to theoretical models, there are some quantum gravity models that predict that you should observe both effects, so a time delay and also a cutoff. But this is not the case if your Lorentz invariance violation happen to be a deform. Not a, if you deform the Poincare symmetry, and instead of breaking the Poincare symmetry, you should not expect this cutoff effect. So in a certain sense, time of flight effects are more general than cutoff effect, because there are cases in which you shouldn't expect any cutoff, but still you should expect a time delay in the gamma rays.
Thank you very much. Yeah, so, but when you showed this table where the Fermi has the best currently best limits, yeah, Fermi observation of a GRB, then this is kind of discipline for itself, and then quantum gravity limits obtained from the cutoff. It is another table, and then but we do not compare two tables because of what?
Yeah, these are all results obtained by time of flight analysis. So they usually
but it is about but it is in the end it is about the same effect, right?
Yes, yeah. This one is about the same effect. So time delay in the gamma rays. Indeed, this as you can see here, you have many of these are gamma ray bursts or HE1 in which you have a flare, so that you have a variability in your data set.
So then I think gamma rays from a source on absolutely very great distance can collect just a delay time of 10 seconds, 20 seconds, while coming to us over billions of years. Yeah.
Yeah.
Okay, interesting. Is there any other question to Giacomo? No, thank you very much, Giacomo.
You're welcome. Thank you.
Yeah. So we switch to the last talk of our session. It is by Martin Tluchikont. Martin, I would like to invite you for a presentation. Martin is going to talk about the TAIGA experiment.
Thank you very much for your introduction, and also thank you, Rasmik, for the invitation and the opportunity to present our results here. I think you should see my slides, and it should be full screen now. Okay, so I want to present our current status and first results from TAIGA. Oh, the title slide was wrong. I'm sorry. This was from a different conference. So we are, with our experiment, we are located at the Tunca Observatory site. There are several components or several experiments going on. In principle, this site has very high energy astrophysics experiments under extreme conditions. It is in proximity to the Lake Baikal neutrino experiment. And this is the approximate location here at the western tip of Lake Baikal that you see here. And so on the site, we have air Cherenkov arrays, particle detectors, and also optical astronomy. There used to be radio air shower detection, which is now not operational anymore. Our collaboration, the TIGER collaboration, first of all, TIGER stands for Tunka Advanced Instrument for Cosmic Ray and Gamma Ray Astronomy. Our collaboration consists of several institutes from Russia, Germany, and also Italy and Romania. And what TIGER is in principle made of, or the constituents of TIGER, are these three main components. This is the TIGER high score timing array, which by the end of this year should reach 120 stations size. Then we have the TIGER IACTs. We have 2 IACTs in operation currently and have a third one in construction. And then we also have under construction a TIGER muon array. Currently 240 square meters of surface and underground particle detectors are available. So in principle, when we talk about the hybrid approach, of course, you have several components. You have air Cherenkov and you also have particles. But what we really mean by hybrid is to combine 2 techniques for air Cherenkov astronomy. And the idea is to have a cost-efficient instrumentation of large areas. In order to do so, what you need is you want to cover a very large area. And one argument that I always take is the number of channels per square kilometer. If you take classical IACTs, imaging air Cherenkov telescopes, you would need many channels to instrument a large area because of the size in number of channels of the cameras. And these stations that we call the high score timing array here only have 4 channels, Gs just 4 PMTs, and then you can instrument much larger areas at a lower cost in channels. Now what we want to do then is to use the timing array together with IACTs, but these IACTs will operate in monoscopic mode, and the IACTs will just provide the image shape. The high score timing array will provide a good angular resolution and core resolution, and this together combines then the strengths of these 2 techniques. And for example, the hybrid scaled width can be used, or we can also recover images that are lost from air Cherenkov telescopes if you use a monoscopic telescope in operation, the monoscopic operation mode. Now, to explain this method a little bit further, what you see here on the left side is the classical stereo operation. So you have symbolically the cameras in the observation plane here with the classical reconstruction of intersecting the major axis. For this, you need the 2 telescopes to be within the air Cherenkov light pool, which is roughly 100 meters, depending, of course, on the energy. It goes up with energy. Now, if you only have these, if you only have telescopes, then you need to space them with this spacing of 100 meters apart. But if you want to instrument a very large area, then this will come at a very high cost. So what we want to do is to do this hybrid imaging and timing technique, where we only consider 1 telescope. And this one telescope, as you can see here down on the right side, will stand in the light pool, but also some of the stations of the timing array will stand in the light pool. And then you see here, you have the image with the major axis. You cannot intersect the major axis with any other major axis, but you can intersect it with the core position from the stations that, from the stations that are shown here with the colored station showing the triggered stations. So the consequence is that you can put the telescopes far apart from each other, effectively instrumenting a larger instrumented area with the same amount of telescopes. And the nice thing is also that at very large core distances, the core resolution will remain the same. Sorry. Excuse me. The core resolution of the high score timing stations always remains the same, even if you are at 300 or 400 meters from the telescope. So if you look at the sensitivity of the Taiga pilot complex, which consists of roughly a 1 square kilometer instrumented area with 3 ICTs, then you end up with this red curve here after 300 hours of observations. Now, if you compare these sensitivity curves to other sensitivity curves, it's always very difficult because we have different fields of view from different types of experiments. And also, even within Taiga, the 2 instruments have quite different fields of views. Now, what I also want to always emphasize when we compare sensitivities is that the key to source identification and to morphological studies is the angular resolution and the relative energy resolution, which, using the Cherenkov technique, is of the order of 0.15 degrees or better than that at TV energies, and of the order of 15% at TV energies, getting better with energy. The scientific goals of the Taiga pilot complex is to establish this new hybrid imaging and timing approach, and then to study TV and PV gamma ray astronomy spectroscopy, meaning that we want to extend the gamma ray spectra into the 100 TeV range with the spectroscopic resolution, and to search for galactic pevatrons with the spectroscopic resolution of 15%. In the cutoff energy range of the pevatrons, as well as morphological studies at 0.1 degree angular resolution. Of course, monitoring of bright extragalactic sources and fundamental physics, as we have heard about in the past talks, are a topic as well. Now I want to go into some details of the instruments. First of all, we have the high-score timing array, of which you see several stations here in the sunset. And what are they consisting of? So each of these channels consist of a PMT here in the bottom in this cylinder. On top, you have a Winston cone, and then you also have a plexiglass plate on top. They are tilted in order to cover a larger sky area, and so we are using a sub-nanosecond area-wide time synchronization, which is very important for the angular resolution. What you see here on the bottom is the sampled signal, which is sampled using a DRS4 chip. And what is used for reconstruction is the amplitude and the timing of the signal. High-score first results have been presented in the past on several occasions. First of all, of course, such an instrument can be used for cosmic ray physics studies. So what you see here in these magenta stars is the spectrum of the high-score stations, which connects well with the Tunka 133 and also agrees well with the data from other experiments. Then we did study the angular resolution in Monte Carlo and verified this angular resolution with using data using the chessboard method. This is shown basically in the plots below. So you see the Monte Carlo energy on the x-axis here. Here you see the station multiplicity, and this is the angular resolution as a function of energy or multiplicity. The single station trigger rates could be reproduced, yielding an energy threshold of 50 TeV for high score. And it was a very interesting discovery in data that the CATS LiDAR was observable. So it's a LiDAR system on board the International Space Station. And so we discovered a point source moving in the sky, which then was coincident with the ISS. This allowed us to actually to calibrate our absolute pointing, which is very useful. The IACTs of Taiga, here what you see is a picture of a photograph of the second IACT. So these are 4.3, roughly 4 meter class telescopes, consisting of 34 glass mirrors with a diameter of 60 centimeters. The facets are adjusted manually because it's not so many facets, so we can use a manual adjustment. The cameras consist of XP1911 PMTs. The first camera has 560 PMTs, and the second one is 595. So with a cathode area of 15 millimeters and a single aperture of 0.36 degrees, we have a threshold, an energy threshold of the order of TeV. So if you look at the camera details, what you see here on the left side is the Winston cone plane. One of our issues is a bit that the Winston cones are not optimally designed, so you have quite large light loss between the cones, which is in principle making the energy threshold a bit higher than we would like it to be. So this is the symbolic representation of the plane. Then each of these, so there are groups of 28 PMTs in the camera, and each of these 28 PMTs is then read out with this Maroc 3 readout board, which has 64 channels. It's using a fast shaper for trigger and a slow shaper for the signals. So there are some details here. I will not go too much into the details here. There has been, there is a pointing correction system installed. What happens is that you have shaft encoders on both ICT axis, but you also have a CCD camera for calibration using bright stars. The accuracy could be shown to be of the order of 0.02 degrees, absolute pointing precision. It was also verified using a kind of drift scan of a star through the central pixel. So what you see here in color scale is while the star goes through the pixel, the current increases to a maximum in the center and then decreases again. And okay. So now I want to go to show some data from the first Tiger ICT. So this is actually the first ICT. It has round mirrors and not hexagonal mirrors. And so you see one of the images here. This is a elliptical image from real data from the first ICT. And the star that is shown here is the reconstructed direction from the high-score array. So this hybrid idea, this hybrid method I was talking about in the beginning, is demonstrated here already to, in principle, work. But so far, we only have analyzed the data from the single telescope in standalone mode in order to understand the telescope. So for us, it's the first step to go there to say, okay, we understand the first telescope, we detect something with the first telescope, and we can go to establish the hybrid method now. So in order to understand the telescope, we look into Monte Carlo simulations. We have two independent simulation chains. You see here a distribution of the second hottest pixel, which is a robust method of comparing. And the blue histogram is Monte Carlo, the yellow one is data. This is from another, the second or first, whatever you want to call it, simulation chain. This is a data and Monte Carlo comparison of the image width, which also fits. We also looked into the differential spectra of the size of the image, which could also be well explained by Monte Carlo. Then just one slide on the Tiger muon detectors. Each of these detectors is a 1 square meter detector with scintillation material and wavelength shifters that then feed the light from the scintillation material onto PMTs. The mean cosmic ray muon amplitude is of the order of 31 photoelectrons with an error of 20%. So we observe a clear muon peak in the instruments. So I want to show the results from the data analysis of the Crab Nebula of the first ISCT. What we do is we only show here the results from a single monoscopic telescope. There is no hybrid analysis yet. This will be done, this is work in progress. So we have two independent raw data reconstruction chains, meaning the way from raw data to image. Then we have 4 groups in the collaboration which are using these data reconstruction chains to do high-level analysis. And we also have first machine learning analysis attempts, which I will not show here. And these are already the results from the observations of the Crab Nebula with the first ICT. So you have to keep in mind here that the Crab for our observation site culminates at 30 degrees. We have a total high-quality data set of 40.5 hours going into this analysis here. The size cut used and other cuts used yield a threshold of 4.5 TeV for the single telescope. What you see in this plot is the distribution of the alpha angle. The alpha angle is the angle between the major axis and the position of the source, meaning that at low alpha angles you expect an excess if you have a gamma ray source. And this is exactly what you is seen in the on data as compared to the red line showing the off data. So you see a clear excess in the on data. There is a journal publication in preparation and will be upcoming. So this is my conclusion slide. I still have time to go through the conclusions because I hear some notifications, but I'm not sure if it's you or if it's something else. Cosmic.
No,
So
you
I will
have
just
time.
go.
Take your time.
Okay.
You were using just 15 minutes until now.
Okay. So I was a bit too quick. Sorry. So conclusions. We have our Tiger pilot complex of 1 square kilometers, roughly, which implements the cost-efficient hybrid timing and imaging Erz-Schrenkow technique. Currently, we have 89 stations and 2 ICTs operational. Yes, I mean, these details, I went through all these details, but I think that one important message is that for both detector components, the Monte Carlo and the data are in agreement. Our first results from the ICTs are that we detected the Crab Nebula. Now the next step, knowing that the Monte Carlo and the data are converging, and we detect a known source, then it means that we can go ahead and make the hybrid event analysis work and prove that this principle of operation works. Then if you go to higher energies, the muon component of Tiger, which I didn't talk about much, will help us to also improve the gamma hadron separation at energies beyond 100 TeV. And finally, in future, what we envisage is to have an order of 10 square kilometer array with 1,000 wide angle stations, high score stations, and 15 IACTs. So if you look at the sensitivity curves here, you see that the 1 square kilometer array is at this sensitivity level. And then if you go down, if you go to the 10 square kilometer array, then you go down to this area, which is just sketched as an area down here at the level of 10 to the minus 13 photons per square centimeter in seconds. Yeah, that's it from me. Thank you very much.
Thank you very much, Martin, for this presentation. I have an immediate question concerning this red strip what you show for Taiga 10 kilometer. I am not able to understand why Taiga 10 kilometer shall be worse than Lasso. Can you please try to explain it? Even if you are keeping in mind that there will be surface detectors and then underground detectors, then it is becoming comparable to Lasso in some sense. So why it
That
should
is
be
true.
significant?
Yeah, so one aspect to really note here is that the sensitivity curve shown here and this estimate of where we would end up is only considering the IACTs and the high score stations. That means that if you study the combination with the muon, with detecting also the muon component, then you would go down, especially at the higher energies, you would go further down than what is shown here with the red area of the 10 square kilometer array.
So this was just to demonstrate that the sensitivity will be comparable to CTA at highest energies, but keeping in mind that also surface detectors and underground detectors will be installed, and it will go further down. I understood. Thank you very much.
Exactly. That is the point. I mean, because so far the studies have only been done for the Erz-Schrenkow part for the sensitivity, and then yes, correct.
Is there any other question? I do not see any other. So we came to the end of our good.
I think someone is talking, but I don't hear anything, actually. I just hear very faint.
Someone is talking. No, not so much. Yeah. Anyway, so I would like to cordially thank all presenters and then thank you for attending this session.
We don't hear you, Razmik.
Yes. Oh, you don't hear me. It is my computer. You know, sometimes it depends on the distance. Yeah, I move my head a little bit back or forth, forward, and then it's changing. Now you hear me. Yeah. Yeah. So I said I would like to thank all of you for participating in this session. Yeah. And then especially I want to thank speakers who talk about diverse topics, very different ones, but I think all of them were very interesting. And with this one, I would like to close this session. Yeah. Thank you very much for attending, for presenting.
Thank you very much for organizing.
Thanks. Bye-bye.
Bye. Bye.
Bye.
Thanks. Bye.